Okay, we're talking about Notebook 20 and linear regression. So if you'd like to go ahead and make sure you get Notebook 20 open. And what is linear regression? So we've done scatter plots, which is the first step. But a linear regression is a way to assess scientifically if there's a connection between two numeric variables. And if there is, we say a correlation exists. And it's important to note that we're not looking at any kind of relationship. A linear regression is talking about whether or not a linear relationship exists between the two. Okay, now, after I do a scatter plot, the linear regression, the stats.linregress test, will actually produce three things. It's going to give us the correlation, it's going to give us a p-value, which is going to assess the significance of that correlation, and it's going to give us the equation of the line of best fit, which Python in the scatter plot calls the fit line, fit underscore line. Okay, and the code is very straightforward. And I want to make this clear that the x variable goes in first and the y variable goes in second, same as the dot scatter method when we're doing the scatter plot. And we need array data, just like the t-tests. We need to use a dot where and a dot column to go ahead and select these groups as arrays and then put the array data in the stats.linregress function. Okay, let's take a look at the first example here. All right, so the first question is SAT scores. Do the math section scores on the SAT correlate with the scores on another section, let's say critical reading? All right, now the hypothesis setup can go one of two ways. So this is the lowercase Greek letter rho, which is essentially like the, it's an analog to the R in our alphabet, the R. So this is basically saying, is the correlation zero? And if the correlation is zero, then the two variables are not connected. There's no relationship. It's only when the correlation is significantly different than zero, right? When we reject the null, that we have evidence for a connection or a relationship between the two. All right. I'll also note that sometimes you'll see this set up, and in the notebook, it is the null hypothesis of beta 1 equals 0 and beta 1 not equal to 0. Either way is correct. We tend to use this one in the notebook, so I've used it here on the presentation slide. What's the difference? Well, this one says the slope of the fit line is 0, which is also true when the correlation is 0. When the correlation is 0, the fit line slope is 0, and vice versa. So we can check either one. And again, I went with the one that we use in the notebook. So let's take a look in the notebook. All right, and let's initialize. And notice that we are importing scipy.stats as stats. I've done that here. And you may just have this one. I like doing this, and then it makes life easier. All right. Now the linear regression equation, so the first thing they do is they read in the table and sort based on state, and then they do the table dot scatter. Critical reading is the x variable. Again, whichever goes in first is going to be along the x-axis. And then math goes in second, so math is along the y-axis, and we've done fit line equals true. Now, earlier this semester, I said that this is an option that I usually only turn on when the pattern isn't clear. Here, the pattern is very clear with or without the fit line. We have a very tight grouping of the points along a very linear pattern. The linear relationship seems assured, but a lot of times it is very helpful to produce the fit line because it will help us see a trend that is otherwise perhaps difficult to see. Here, we're going to check it out, and we'll see some interesting things about it a little later on. So it turns out that we can calculate the line of best fit and we can calculate the slope. It's the correlation times the standard deviation in y over the standard deviation in x, and the y-intercept is calculated as this. And is this important? Do you have to memorize this? No, but this is where it all comes from. And here we go. We are taking the table now, and we're ready to employ this stats.lin regress. So since I imported the scipy.stats as stats, this will work. You may need the scipy.stats. And when I run this, I get tons of output. And like I said, we get three things. So the first thing I get the slope and the intercept for that line of best fit, right? And so the line of best fit is in the form, if we go back to high school, y equals mx plus b. That's what we used, where m is the slope and b is the y-intercept. And we've got the values right here to create that line of best fit. Okay, we also have the correlation here, the R value, the correlation. And look, the correlation is very strong. So correlations can range between +1 at the top and -1 at the bottom and 0 in the middle. So 0 is where there's no correlation at all. And the further I get towards +1 or -1, the closer to perfect fit or perfect correlation that I have. So this value very close to +1 is a strong positive correlation. And then look at the p-value. The p-value initially looks like it's about 6.9, but notice it's times 10 to the -39th power. So we are going to have a value here that's very, very close to 0. So let's just glance back at our notes and see if we can make a note, make sense of all this, right? So yes, do we get tons of output? Yes, we do. Okay, the standard error is useful in some more advanced statistics applications. So it's not going to worry us right now. The key things that we need are the correlation, p-value, and then these slope and intercept for the line of best fit. Those are the important values for us. Okay, and what we're assessing here, right, with the p-value is this hypothesis. So let's jump ahead to the next slide. Okay. Oh, sorry, I jumped ahead to the next result. So what's going to happen here? We have a small p-value, right? So since p is essentially equal to 0, which is less than alpha, right? We're going to reject the null. Why? Because it's very unlikely to be true. We're going to reject the null, and we have evidence for the alternative. We have evidence that there is a significant correlation, right? So there is a significant correlation, which means, and I'll just say R for correlation, right? That correlation coefficient is significantly different than 0. That's the way we're going to report this out. And if we jump back into the notebook, those things are stated explicitly for us, sorry. Right? Except the formula goes through and actually calculates the different values that were shown above in the theoretical section and actually calculates everything and notes that, hey, it comes out exactly the same. Here they produce the line of best fit from the theoretical calculations and superimpose that on top of the scatter plot, sorry. And what happens? Well, essentially the same exact thing. It looks nearly identical to before because, again, the formulas were correct and the theory was correct. So the last few blocks of code just show that. And they go through and show in a couple more ways that things are, in fact, the same. Here, they show both versions of that hypothesis test. Again, we can use the rho equal to 0, rho not equal to 0, beta equal to 0, beta not equal to 0. Either one is fine. Okay, and then let's check the reporting out. Right, so we know that the correlation and the slope of the regression line are significantly different than 0, right? So we have a significant correlation. And how do we know? Well, the p-value is even less than 0.001. Okay, so we have rejected the null, right? Reject the null. We have a significant non-zero correlation, and that correlation is also positive. Okay, and right there. So that's how we're going to report it out. And what are we showing here? We're showing the same thing, except now we have the line of best fit written in terms of the y variable, which is math. Score on the math section is 0.99 times reading plus 7.36, where reading is the x variable score from the critical reading on the SAT. All right. And now we have a very strange hypothesis test. You may have seen this when I flickered to it before. So the question was mask compliance linked to higher rates of COVID-19 deaths in Europe? Okay, and we're like, what? Wait. Okay, so we're going to check to see in this data set from countries in Europe, we have an estimate of the compliance with the mask mandates, the mask recommendations from the different governments. And we also have deaths attributed to COVID-19 in those countries. Now, I don't want to start a political debate about masks or COVID-19, but this is an interesting data set. And let's just take a look at it and note we're checking to see, is there a correlation? Maybe not, right? If the null hypothesis is 0 correlation, and the alternative hypothesis is, hey, and not a negative correlation. In other words, if masks were preventing deaths due to COVID-19, we'd expect a negative correlation that higher compliance with mask mandates would lead to more prevention of COVID-19 deaths. What we're checking for, according to our according to the information we have so far, is we're checking to see if there's a positive correlation. If, as the mask compliance goes up, the COVID deaths go up. So, like, what? That's sort of a strange hypothesis. And let's take a look at this data set. Okay. This is the mask data, and you can see that the countries in Europe are listed. The compliance is a decimal number between 0 and 1. So we have up 53% in Albania and 40% in Bosnia. And then we have the deaths due to COVID-19 and the number of cases. All right. So we do what? Well, we're dropping country and cases. Why? Well, because we want to do compliance versus deaths. That's the correlation we're checking. So if we drop the other two when we do scatter, we just name the x variable compliance. We do fit line equals true. And whoa, okay, so first of all, the first thing to notice is this is not the same tight, strong relationship that we saw in example 1. Example 2, the scattering of the dots is a big dispersed cloud. And so the fit line equals true really does help us pick up this trend. In other words, with the naked eye, is it easy to see this trend? And I would suggest no. And once we see the fit line equals true, the dark blue line there actually has a positive slope. So what we're looking at is a potential positive correlation. That's the association we're seeing. So the association we're seeing in the graphics here, the association is, hey, it looks to be a positive correlation. So that's the association. We don't know anything yet. So what are we going to do? We're going to run stats.lin regress. Okay, so notice that we go in and we go mask.column compliance, right? The dot column, why? Because we need array data to go into the stats.lin regress. Okay, and then mask.column deaths, all right? So compliance is going to be our x variable because that's the array that goes in first, and deaths is going to be our y variable, okay? And then we spit out the results. And again, it's a big, long batch of numbers. Let me identify a few for them for you. First of all, notice that the correlation is 0.3. okay? And I probably should use an approximately equal to, but we are not talking about a big value close to 1. Even if this is significant, the correlation is small, right? It's a low amount of correlation, okay? Let's check the p-value, okay? Now the p-value is 0.077. Now, we used a one-tailed hypothesis. We used a directional hypothesis, right? So we get to cut the p-value in half. This is the two-tailed p-value for the alternative hypothesis where rho is not equal to 0. So that p-value is right here. But our alternative hypothesis, sorry, let me draw a rho, is that rho was greater than 0. Since we were using a one-tailed hypothesis, we get to cut the p-value in half to have an accurate p-value. And let's see what that is. Boom. Oh my goodness. So now we have a p-value that is less than 0.05, right? So what we're seeing is that this correlation of about 0.3 indicates that both the correlation and the slope of the regression line are significantly greater than 0 and greater than 0, right? So there is a positive association between mask compliance and COVID deaths. All right, and here is an equation of the line of best fit written in terms of the variables. And I want to jump back into the slides here and just jump here. Do the results mean that in Europe wearing masks increase one's risk of mortality due to COVID? And that is absolutely the wrong takeaway. Okay, it's a rather stunning result, but what we have evidence for is that in Europe, higher compliance with mask mandates did not improve mortality rates. Okay, so we do have evidence that that masks didn't seem to be a really effective cure or preventative option for COVID-19. All right. But I want to mention a couple of things, and you can read the notebook. The notebook also explains a couple of these things. First of all, there are different ways for these variables to be related. For example, suppose there was a high mortality rate due to COVID-19 in a country. That might scare people, and due to the fear for their own safety, the compliance might go up. More people might wear masks because that was the only defense for a long time that we had against COVID-19. So the causation might go in the other direction. Instead of compliance preventing COVID-19 mortality, COVID-19 mortality might scare people and increase the compliance. So we don't know which direction the causation is. And then the key thing to look at is correlation does not imply causation. So this is a very interesting result about masks and COVID-19, but it's presented in this course as an example of actually scientific fact, but be careful about taking one little snippet, one little piece of scientific truth and making more of it than there actually is, right? We need to be conscientious with our claims and also to remember that correlation does not imply causation. What are the key things to know from this lesson? Let me jump back in and say that the key thing is we need array data for the x variable and the y variable. We're going to use stats.lin regress, and we get all this output, right? And we're going to start the linear regression using the dot scatter, right? We're going to use a scatter plot with fit line equals true. So we're going to use the dot scatter method to at least look for the association. So the dot scatter method is going to show a scatter plot. We're going to put fit line equals true. We're going to check to see if visually there appears to be any association whatsoever. If we do see some association, then we can set up our hypothesis test and use the stats.lin regress to check for it. This is on the final project, guys. So linear regression is one of the things we're going to do on the final project. So I wanted to kind of reiterate the key ideas here at the end.